Welcome. This video will derive the formula for time dilation in special relativity. For this derivation, I'd like you to imagine a light clock, except not this sort of light clock, a more conceptual light clock, as shown here. This light clock is made out of two mirrors separated by a distance d. You have a beam of light between the mirrors, and the light bounces from one mirror to the other mirror. This is a clock because the time it takes for the light to travel from one mirror to the other mirror is considered one quote-unquote tick. So, this derivation will require basic physics and basic math. Essentially, you only have to know two formulas. That distance is equal to velocity times time, and Pythagorean's theorem. Time dilation occurs because in special relativity, the speed of light is the same in all reference frames. That means that if you stand still and you're in the same room as the clock and you're moving at the same speed, the speed of light will appear to be the same in the clock as it is to an observer who's traveling at a different speed than you are. Since this velocity term of light is always constant, you'll find effects of time dilation and length contraction. In this case, we'll notice that the time increases in proportion to distance, and vice versa. Now, we'll rearrange this equation to get time on one side, and that equals to distance over velocity. We'll denote the time of one tick of our light clock to be delta t0, which is the time it takes for the light to travel from one mirror to the other mirror. So this should be equal to the distance d between the two mirrors and c, the speed of light. If we rearrange this equation for d, we'll get that d is equal to c times delta t0, which we'll use later on. So now imagine that the light clock is indeed on a train, and it is moving at a speed u. You are an observer outside of the train. This is our new model. Before, our light was traveling at a distance d between the two mirrors. This would be the observation of someone inside the train. To an observer outside the train, the light now travels a distance L in purple. This is because there is now a horizontal velocity added to this light. The vertical distance remains the same, and it is d just like before. If we denote the time that it takes for the light to now travel between the two mirrors as delta t, we'll notice that the horizontal distance is now the speed u times its delta t. So, now we'll use Pythagorean's theorem, and the vertical distance traveled is d, and the horizontal distance traveled is u delta t. So, by using Pythagorean's theorem, we can solve for the total distance L, which is the square root of d squared plus u delta t squared. Expanding this u delta t squared gives us u squared delta t squared over here. Reusing our time equals distance over velocity formula, we get delta t is equal to L over c. Expanding L, we put L right here, as before, and we leave the 1 over c outside. Earlier we derived that in the previous reference frame, when you're standing inside the same room as the light clock, we had d is equal to c times delta t0. So we can substitute this t delta t0 into our equation right here for d. We do that, and over here you can see this c squared delta t0 squared. We want to get rid of the square root over here, so we square both sides. This delta t becomes delta t squared. This 1 over c becomes 1 over c squared, and we have removed the square root. We distribute this 1 over c squared, and we get delta t squared plus u squared delta t squared over c squared. We notice that this delta t squared appears here and here, so we subtract this bigger term to the other side over here, and then we factor out the delta t squared, like so. We isolate the delta t squared by dividing by this larger term, and we get this expression. Finally, we get rid of the squares, so this square goes away and we get delta t, and we get delta t0, and then we get square root of 1 minus u squared over c squared. To remind you what each of these terms are, this delta t0 is the time it takes for the light in the clock to travel if you observe it from inside the train. This delta t over here was the speed of an observer outside the train, and how long they observed it to take the light in the clock to travel the distance L. And this u squared over here was the horizontal speed of the train, and c was the speed of light. Let's see how this works. So here are some examples. Let's say u equals 0. This is the case for when you are inside the train with the light clock and there is no horizontal speed. If u equals 0, this u squared becomes 0, and we get that delta t equals delta t squared, delta t0. And we notice no special effects from special relativity. Typically, we'll only notice effects when the speed becomes a significant portion or fraction of the speed of light. So let's say u was 1/2 the speed of light. Then we plug this 1 over 1/2 c over here for this u, and you see this 1/4 c squared over here. If we use a calculator, we'll see that delta t is now equal to 1.15 delta t0. So this makes sense, because if you go back to our diagram before and look at L is bigger than d, so we know that the overall distance traveled increased. Since the speed of light was constant, then the time must also increase. so the time increased by 1.15. Similarly, if we go to an even more extreme case, where u, or the horizontal speed, is 0.99 times the speed of light, we get that the time by an observer outside the train appears to be 7 times as large as is inside the train. The net effect of this is that an observer outside the train sees that time inside the train seems to appear much slower. Special relativity can take some time to get used to, but it's an interesting topic, and I hope you enjoyed this derivation. Thank you, and have a great day.